Today we're going to learn how to graph rational functions. Now we've learned a lot about rational functions, how to find the horizontal asymptotes, the domain, the vertical asymptotes, oblique asymptotes, all of that. Now we're going to put all of that together, plot some points, find intercepts, and that's going to help us sketch a function. So to graph a rational function, we're going to have about 4 steps we need to take. And here's step 1. The first thing you want to do is you want to factor the numerator and the denominator. And then you want to find the domain. So when you factor the denominator, that will give you the domain. You just set each factor equal to 0, solve for x, and then you'll get the domain. After you do that, your next step is to write your function in lowest terms. That means if you have a common factor in the numerator and the denominator, you want to get rid of those. And you want to do that after you find the domain. Once you write your function in lowest terms, then you can find your vertical asymptotes and your holes. I'm going to abbreviate vertical asymptotes to VA. So your vertical asymptotes will be whatever's left over in the denominator once you simplify, so you got the function in lowest terms. The holes correspond to the factors that you got rid of in the numerator and denominator. That will give you the x value, and then to find the y value, you just plug that x value into your simplified function. And we'll see that a little bit later. So once we find the vertical asymptote and holes, we want to graph the vertical asymptotes and holes. And these vertical asymptotes will break your graph into sections. So use the vertical asymptotes. Make that a little bit smaller. So use the vertical asymptotes to break the plane into sections. And I'm going to show you how to do that a little bit later. I'm just giving you all of the steps we need to take first. Okay, after we do that, the next thing we want to do is to find the horizontal asymptote or the oblique asymptote. So find HA stands for horizontal asymptote or oblique asymptote. And then we want to graph that asymptote if it exists. And remember, we can only have one horizontal asymptote or one oblique asymptote. We can't have both. Okay. Then the last thing we're going to do is we want to plot the x and y intercepts. And we can use the multiplicity of those intercepts to help us sketch the graph. And we're also going to plot a few additional points to help us sketch the graph. And I'll show you how to do that too. But these are the main steps. And while we do some problems, I'll walk you through each step and what we need to do, all the little pieces that we haven't written here, such as like what points we need to pick and how we can sketch the graph from just a few points. Okay, so let's look at our first example. I want to graph this function. r of x is equal to 6 over x plus 3 times x minus 4. So the first thing I'm going to do is I'm going to draw a plane. Okay. Now that I've done that, our first step was to factor the numerator and the denominator. Notice that the numerator, you can't factor any further, nor can you factor the denominator any further. It's already factored for you. Let's find the domain. Now remember, the domain is all the x values that you can plug into the denominator. The only things we can't plug in is -3 and 4, because that will give us 0 in the denominator. And of course, you can write this in interval notation. I believe we've done this before. I'm going to write it one more time, because we've seen this function in another video. Okay, so we found the domain. Now, if there was something to cross out in the numerator and the denominator, we would do that now. But because this is in lowest form, we don't need to reduce this any further. Now we're going to find the vertical asymptotes. Well, the vertical asymptotes, there's 2 of them, and they're x is equal to -3 and x is equal to 4. Let's plot those 2 vertical asymptotes. So what we're going to do is we're going to move out 1, 2, 3, and 1, 2, 3, 4. I'm going to make a dotted line at x is equal to -3. I'm going to actually write this up here. And also at x is equal to 4. Now notice that I've divided the plane into 3 sections right now. Okay, so we would write down any holes that we'd have, but because we didn't reduce this, we don't have any holes for this problem. Now we're going to find the horizontal asymptote or the oblique asymptote, if it's possible to find one. How we do that is we look at the degree of the numerator and the denominator. Notice that the degree of the numerator is 0, because this is just the constant 6. You could think of it being multiplied by x to the 0, which means the degree is 0. This one's a little trickier. You could FOIL this out if you wanted to, but remember, we only need the highest power on the x. So if you multiply this one with this one, you're going to get an x squared. And then you're going to get some other stuff, but this will be the leading term, so the degree is 2. Because the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote. And that horizontal asymptote is y is equal to 0. So let's put a dotted line at y is equal to 0. Remember that the horizontal asymptote tells us the end behavior of our graph. Okay, so I'm going to do a little bit of erasing because I need some space over here. Just make sure you copied all of that down. Okay, so remember, with vertical asymptotes, we cannot cross that, but we can cross horizontal asymptotes. I'm going to put y is equal to 0 here for our asymptote. Let's find the x and y intercepts. Now, how do we do that? So recall that a y-intercept is where we plug in x is equal to 0 into our function. So I'm going to do that. R of 0 is equal to 6 over 0 plus 3 times 0 minus 4. So we get 6 over -12, which is -1/2. So we have the y-intercept of 0, -1/2. Let's put a dot. I'm going to actually do this in blue. At 0, -1/2. So if this is, let's say this is 1, 2, 3, 1, 2, 3. Here is our y-intercept. So jot that down, put a little dot. Now let's find our x-intercepts, if we have any. So remember, to find an x-intercept, we set y equal to 0. In this case, this is r of x. And then we solve for x. So I'm going to set this equal to 0. And now just multiply both sides by the denominator. If you do that, you get 0 is equal to 6. Okay, this is not a true statement. 0 is never equal to 6. So we're not going to have any x-intercepts. Okay, so just multiply by what you have in the bottom. If you had something involving x here, you get that something involving x equal to 0, and you would solve for x. Because there's no x, we don't have to solve for x. We got a false statement, so we have no x-intercepts. So what does that mean for us? That means we do not cross this, this x-axis here. This line y is equal to 0, we don't cross it. Because if we crossed it, then we would have x-intercepts. So we need to keep that in mind when we draw our function. Now let's think about what's going to happen. Remember that the line here, this horizontal asymptote, determines end behavior. It tells us what our function is going to do on the ends. Now, we're either going to go towards it at the top or at the bottom like this. And then over here, we're going to head towards this asymptote. So the two options we're going to have is this one or this one. We're not going to cross this line because one is the asymptote and we didn't have any x-intercepts. The graph of a rational function is always smooth. So when you have terms, you're going to make nice rounded edges. Remember that when you have a vertical asymptote, you do not cross that asymptote. And you always go towards infinity or negative infinity. How we can figure out which one we have is we just plot a point in one of these areas. So let's pick something that's smaller than -3. That's to the left of -3, like -4. Let's see what happens when we plug in -4 into R. So if I plug in -4 into this function, I get 6 over -4 plus 3 times -4 minus 4. And really all I care about is if I get a positive or a negative number. So let's say we get 6 over -1 times -8, which is 6 over 8. So what that tells me is 6 over 8 is bigger than 0. So that's above this y is equal to 0 line. So it's somewhere like right here. So at -4, we get the point -4, 6 over 8. 6 over 8 is a little bit smaller than 1. Okay, so what this tells us is that to the left of this point, in this area here, we're not going to cross this line, but this is an asymptote, so we're going to go towards it. Let me do this in blue, like that. And then on this side, we got to think about all the options. Our function has to go towards this asymptote because remember, it is an asymptote which tells us that when we get close to it, we either go to infinity or negative infinity. Because we cannot cross this line, we're going to go up towards infinity. Okay, so that gives us this portion of the graph. The next thing is we need, well, technically we don't need to find any more points here because I'm going to tell you what's going to happen. Again, over here, this portion of the graph is going to have to go towards either negative infinity or positive infinity. Now, because we can't cross this line, it has to go this way because this is an asymptote. And then we're also going to go this way. And the graph could go a little bit up like this. What we're doing is we're sketching a graph, so it doesn't have to be perfect. We just need to get the idea of what happens with this function. Of course, it could go a little bit up here, but it would have to go downward and a nice smooth turn down like that. So what I'm going to do to sketch this graph, remember this is an asymptote, so they're either going to have to go up to infinity or down to negative infinity because I can't cross this line. I'm going to go down to negative infinity. Okay, and now I just need to graph something on this side here. So what I'm going to do is I'm going to plug in something bigger than 4. So let's go with 5. So if I plug in 5, let's see what happens. So if we plug in 5, we get 6 over 5 plus 3 times 5 minus 4, which is 6 over 8 times 1, which is 6 over 8. Okay, so we're going to plot this point. We've got 5. We're going to go up 6 over 8, which is close to 1. And here's a point. If we go to the left, remember this is an asymptote, so we have to go up like this towards it. And then on this side, this is an asymptote, so we're going to go down like this. And so this is our graph. You can see that we have something in each section of this, this graph here. We're going towards asymptotes. And yeah, this is what the graph's going to look like. Now let's compare this to the actual graph. So I'm going to use a graphing calculator to look at this. So give me just a second. I'm going to switch over to Safari. Okay. I'm going to type in this function. It is r of x is equal to 6 over x plus 3 times x minus 4. Now, doesn't that kind of look like this graph? You can see right here that this wasn't exactly the maximum like I had sketched, but that's okay. I'm just looking for the idea of what the graph looks like. So we definitely have asymptotes here, just like we expected. It looks like it is -3 and 4. And then we have this horizontal asymptote, y is equal to 0. Okay, let's go back to our pad here. Let's move on to another problem. So this is the second problem. F of x is equal to x minus 1 times x minus 1 over x squared minus 4. So we want to graph this rational function. So I'm going to do exactly what I did last time. First thing is we're going to factor the numerator and the denominator. The numerator is as factored as you can get it. The denominator factors into x minus 2 times x plus 2. Okay, I'm going to go ahead and start making a plane. Okay. All right, so what is our domain? Our domain is everything but positive and -2, because we can't plug those into the denominator. Our vertical asymptotes, we can find that from here because we don't have to reduce anything. We can't really reduce anything. So the vertical asymptotes are x is equal to 2 and x is equal to -2. So I'm going to draw 2 dotted lines at -2 and at +2. So notice that we broke the plane into 3 pieces. Now let's find our horizontal asymptotes. To do that, we just look at the degree of the numerator versus the degree of the denominator. The degree of the numerator is 1. The degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at y is equal to 0. So let's plot that. Great. Okay. Now the next thing that we want to do is we want to find some intercepts. That's going to help us draw this graph. So let's start with, I think the y-intercept is always the easiest to find. So the y-intercept is where we plug in x is equal to 0. So if you do that, f of 0 is equal to -1. I'm plugging it into this function over -4, which is 1/4. So we have the point 0, 1/4. Let's put a dot there. So we just really need to get an estimate here. So let's say that's the point. This is like 1, let's say. And now we need to find the x-intercepts. Okay, so to find the x-intercepts, we plug in y is equal to 0, which is this function here. So we just set this equal to 0, multiply by the denominator, this x squared minus 4, and you'll just get 0 is equal to x minus 1, or x is equal to 1, which tells us we have the point 1, 0. So here's 1, so I'm going to put a dot here. Okay, this is the only place that we're going to cross the x-axis. So using that bit of information, let's think about what's going to happen in the middle. Remember that these are asymptotes, so that determines the behavior near this, these asymptotes. We're either going to go up to infinity, like that, or down to negative infinity. Now, this is the only place that we cross the x-axis. So what's going to happen is we're going to touch this guy right here, because we're up here as well, and then we're going to go down towards negative infinity. We can't go up this way, and the reason for that is the multiplicity on this x minus 1, this guy right here, the multiplicity is 1. And remember that when the multiplicity is odd, then we cross. When the multiplicity is even, we touch. If I had x minus 1 squared here, we would touch this graph and go up. So we're going to go down towards negative infinity. And if you're not sure, if ever you're a little lost, like, oh, do I go back up or do I go down? Just plot a point. So something between 1 and 2. Let's say f of 1/2, so 1.5. That will be 1.5 minus 1 over 1.5 squared minus 4. On the top, you're going to get 0.5. On the bottom, well, 1.5 is less than 2, and 2 squared is 4. So this is definitely going to be less than 4. So you're going to get something that is, in fact, I can put this in a calculator just to figure what else what that figure what that is. That is 2.25. So if we subtract 4, you can see that on the bottom we get a negative number. And so then we'll have a positive or negative, which is a negative number, which tells us we're going to be down here somewhere. Now, because this is the only place we cross the x-axis, we're not going to cross and go this way, because then that would be another x-intercept. So we have to go up like this. Okay? The next thing we're going to do is we're going to have to plot something over here and also over here. So let's pick something. If this is -2, we need to pick something a little bit smaller, like -3. We're going to plug that into our function and see if we get a positive or a negative number. So -3 minus 1 times -3 squared minus 4. This will give us -4 over 9 minus 4, which is -4 over 5. This is a negative number, which tells us when we plug in -3, we get -4/5, which is somewhere around here. And we're underneath this, this asymptote here. Okay, so what's going to happen? We have to go towards this asymptote, and we're going to go towards negative infinity, because we can't go this way, we would cross the x-axis. So we're going to go towards negative infinity, and then we have to go towards this asymptote as well, because that determines our end behavior. Now let's plot a point on this section of our graph. So we need to choose something bigger than 2, like 3. So we're going to plug 3 into this function. So we get 3 minus 1 over 3 squared minus 4, which is, this is going to be 2 over 9 minus 5, which is 2 over 4, which is 1/2. And this is a positive 1/2, which tells me when we plug in positive 3, we get 1/2. And we're going to have the same thing happening here, but up here. Because when we go this way, we're going to go towards infinity. We can't cross this axis. And then this side is going to go towards this asymptote. So this is the graph. This is what it's going to look like. So let's switch over to our graphing calculator. What I'm going to do is I'm going to write this function. This is f of x is equal to, on the top, x minus 1, on the bottom, x squared minus 4. And let's compare that to what we did before. You can see they look very similar. Again, the graph doesn't show us the intercepts, but we could draw those lines as well if we needed to. You can see that we're going down like that. We've got something that looks like x cubed, the negative of x cubed, and then we have this part here. Great. Now let's go back. Here we are. Let's do another problem. Here I want to graph h of x is equal to 3x squared plus 1 over 2x squared minus 9x. I'm going to make a plane. Okay, let's factor the numerator and the denominator here. So this is equal to, notice that at the top, you can't factor it unless you factor over the complex numbers. We're not going to worry about that because with the complex numbers, you know, we're just not going to worry because this is the plot on a real number, so we don't graph complex numbers here. And why I'm saying that this doesn't factor over the real numbers is if we set this equal to 0, you'll see that we get 3x squared is equal to a negative 1 divided by 3. We get something squared as a negative, which is not true in the real numbers. So this is a prime polynomial. On the bottom, however, we can take out this x and we get 2x minus 9. So you can see that for the domain, x can't be 0 and x can't be 9 over 2, 4.5. And because this is in lowest terms, our vertical asymptotes are exactly these two numbers. X is equal to 0 and x is equal to 9 over 2. So let's draw two dotted lines at x is equal to 0. I'm going to write that here. And also 9 over 2. So that's 4.5. Let me zoom out a little bit. So x is equal to 4.5. Let's put that here. I don't need this point here. Okay, so now let's figure out if we have any horizontal asymptotes. The answer is yes. We don't need this part to figure out the horizontal asymptotes. We need to look at the original equation. So the degree of the numerator is 2. The degree of the denominator is 2. So the degree of the numerator is equal to the degree of the denominator. That tells us that we have a horizontal asymptote, and the horizontal asymptote goes with the ratio of the leading coefficients. So it's just equal to 3 over 2. The highest power, this part right here, this term is called the leading term, and this is the leading coefficient. So we just take the leading coefficients on the top and bottom, and we divide them. So that's 1.5. So let's make a dotted line at 1.5, but a horizontal dotted line. Okay, and you can see that we've divided this into 1, 2, 3, 4, 5, 6 different sections. The next thing we want to do is find our x and y intercepts. So let's write that down. Okay, so what is our, let's start with our y-intercept. So if we plug in 0, we get 1 on the top, and then, oh, what do we get on the bottom? We get 0, which tells us that we don't have a y-intercept because we're dividing by 0. And also that makes sense because we had a vertical asymptote here and we do not cross it. So we do not have any y-intercepts. What about x-intercepts? Well, to find x-intercepts, we set the function equal to 0. And then we multiply by the denominator to get 0 is equal to 3x squared plus 1. But we talked about this earlier. We said that if we solve for x squared, we get a negative 1/3. And if we take the square root, we get imaginary numbers for values of x, which tells us that we're not going to have any x-intercepts. And that tells us we're not going to cross this line here. Okay? So we need to just graph some points. So we're going to pick a point to the left of 0, to the right of 0, but to the left of 4.5, and then to the right of 4.5. So let's start with, let's go to the left of 0. So let's go with x is equal to -1. We're going to plug this into the function. And I really only care about if I get a positive or a negative number. So if I plug that in, I get 3 times -1 squared, which is 3. And then plug it into here, I get 2, because this -1 squared is 1, minus 9 times a -1, which is 4 over 2 plus 9, 4 over 11, which is a positive number. But 4 over 11, let's see where that is. So this is -1, 4 over 11. So 4 over 11 is smaller than 1.5. So it's actually below this 1.5. So I'm going to put -1 here. And let's say that the point is right here. Interesting. I want to graph more points on this side. So let's choose something else. Let's go with x is equal to -2. So if we plug in -2 into this function, what do we get? We get 3 times 4 plus 1. And then up here we get 2 times 4 minus 9 times a -2, which is 12 plus 1 over 8 plus 18. So 13 over 26. Let's pull out a calculator and get an idea of what that is. 13 over 26 is 0.5. So 4 out of 11 was what we originally got. 4 over 11 is 0.3636. So 0.5, if this is 0.3636, then it's going to be a little bit higher. So when we plug in -2, we're a little bit higher. And so what it looks like what's going to happen, you can plug in more points if you want to. We're going to go up towards this asymptote like that. We're not going to go down because remember, it determines in behavior, this asymptote. So we always have to go towards it. And we can't go past here. So what's going to happen on this side is we're actually going to go up towards this, this asymptote here, because we either would go up or down, and we don't cross the x-axis because we didn't have any x-intercepts. So the only thing we can do is go up like this, and it's okay to cross a horizontal asymptote. So if you want to verify this, put something in between -1 and 0, closer to 0. So let's say put in a half or 0.25. If you plug that in, I bet you're going to be above 1.5. So it's going to go up like that. Okay, so now let's plug in something that is bigger than 0 but smaller than 4.5. I think a nice number to plug in is 1. So if we plug that into our function, we get 3 plus 1 over 2 minus 9. So we get 4 over -7, which is a negative number. Okay, so if this is 1, we're getting a -4 over 7. So it's going to be down here underneath this axis. So what's going to happen? Remember that we always go towards asymptotes. We're not going to go up this way because we don't cross the x-axis. We don't have any x-intercepts, so we have to go down like this. And then on this side, we might be able to go up a little bit or something. But in general, eventually we're going to have to go down towards this asymptote because we don't cross this axis. Okay, now let's choose something bigger than 4.5. So let's go with 5. H of 5 is equal to 3 times 25 plus 1 over 2 times 25 minus 9 times 5. I'm going to put this in the calculator. So 3 times 25 plus 1 is 76. And then we have 50 minus 45. Oh, sorry, I think that's, is that 45? Yeah, 45. So that's 5. So 76 over 5 is 15.2. So when we plugged in 5, which is a little bit bigger than 4.5, we got 15.2, which is way up here. So I'm going to put a little dot like that, which tells me that we're getting close to this asymptote. And my guess is what's going to happen is we're going to come down like this and go towards this asymptote. Now we can verify that by plugging in more numbers. Now it is possible that we go below this asymptote like the other one did. But again, we're just trying to sketch this graph. We don't want it doesn't have to be perfect. You can plug in more points to see if it does pass this line, but I'm pretty sure it doesn't. I think it's going to go like this. So let's graph this. So let's switch over to Safari here. I'm going to erase this and I'm going to say y is equal to, and I'm going to plug in that function 3x squared plus 1 over 2x squared minus 9x. Okay, so let's look at this. Compare this to what we drew. You can see that it looks like we have an asymptote at x is equal to 0, just like we expected. Also around 4.5. I believe we've graphed this function before. And then we have, like we were expecting, something that looked like a hump going downwards in this area. And then if we zoom out, you can see that this stays above that asymptote. Great. So let's go back here and let's move on. So this is the fourth problem we're going to look at. We have g of x is equal to x plus 2 times x minus 1, 2x minus 1, 3x, x minus 1, x minus 2. I went ahead and factored this for you. Again, we've seen this problem before. We actually graphed it on the graphing calculator, but now we're going to graph it by hand without looking at what we did before. So we're first going to start by just drawing this plane here. And let's see what we notice about this function. Okay, so the domain, what values can we not equal? We can't be 0, 1, or 2, because if we plug any of those values in here, we get 0 in the denominator. But notice that when we reduce this, we get rid of that x minus 1. And that tells us that the vertical asymptotes correspond to x is equal to 0 and x is equal to 2. X is equal to 1 is not a vertical asymptote, it's a hole. And let's plot what that hole is in just a second. So first let's plot these two asymptotes. So at 0, and also at 2. Like that. So I'm going to put x is 2, x is 0. Now to find the hole, what you're going to do is you're going to get rid of this piece here. So this new g of x is equal to x plus 2 times 2x minus 1 on the top over 3x times x minus 2. And now we're going to plug in that value, this value right here, 1. So if you plug that into the function, you can't plug it into this one because you'll get 0 in the denominator. But if you plug it into this one, you'll get 3, plugging it into here, then into here, that'll be times 1 over, plug in 1 here, you get 3 times 1 minus 2, that's a negative 1. So it looks like we get 3 over negative 3, which is negative 1. So let's plot that point. So when we plugged in 1, we got negative 1. But what I'm going to do is I'm going to make a circle right here. I'm not going to fill in that circle because it's a hole. We don't have a point defined there. Okay. So we found the hole, we found the vertical asymptotes. Now let's find the horizontal or oblique asymptote. So what does this one have? Now we go back to the original function here. You can take this out. You're still going to get the same thing, but I'm going to go to the original one. We need to figure out what the leading term is. So if we were to FOIL this all out, multiply it all out, we just want to know what the leading term is. So the leading term would be found by multiplying this one with this one and this one. So that would be 2x cubed, 1, 2, 3. Then on the bottom, to find the leading term, is 3x times x, which is 3x cubed. So if we were to continue to multiply this out, we'd have some other stuff, but this would be the one with the highest power on x. And we would have some stuff here, and this would be the highest power of x. So for our horizontal asymptote, because the degree of the numerator is equal to the degree of the denominator, we take the ratio of the coefficients, these leading coefficients. So it's 2 over 3. So let's draw a line at 2 over 3. So let's say this is 1. 2 over 3 is 2/3 of the way. So like this. Okay. Now let's find x and y intercepts. I'm going to clean this up a little bit. Okay. Start with a y-intercept. Now we're not going to have any y-intercepts. Why? Because to find a y-intercept, we set x equal to 0. Remember, that was a problem in the domain. In fact, we have a vertical asymptote here, so we can't cross this vertical asymptote, so we're not going to have any. Let's talk about x-intercepts. For our x-intercept, we plug in y is equal to 0. So if we set this equal to 0, we're going to get x plus 2. Let's go ahead and get rid of this x minus 1 again. Then 2x minus 1 over 3x, x minus 2, like that. Then multiply by the denominator. So you're going to be left with 0 is equal to x plus 2 times 2x minus 1. So you'll get x is equal to -2 and x is equal to 1/2. So you're going to have two x-intercepts, one at -2, 0, and the other one at 1/2, 0. So let's plot those 2 points. So one of them is at -2. So 1, 2, -2, 0 right here. And the other one is at 1/2, 0. So this was 1, so half is here. So we're going to go right here. Okay, so the multiplicity on these intercepts, look up here. Notice that the multiplicity is 1 for both of these, which means we cross here. We cross here. If the multiplicity was even, we would touch and go. So like we might go just touch this and go down, or touch and go up. So let's think about what can happen here. Since this is a function, we have a point here. Remember that the end behavior always goes towards the asymptote. So we're going to go towards this way. In fact, you can put more points if you like. You can go with like -3 or something. You're going to go towards this asymptote here. Let me do a little bit of a better job of drawing that. Like that. And then, because we touch this, and we're not going to go back up past it, and then we have this asymptote here, we're going to go towards this asymptote. Then for this piece, let's see what's going to happen. We definitely hit here, and this is the only place we hit. And then we have a hole here, which tells us that we're going to go towards this hole. And then, because we either go up towards this asymptote or down, we're going to have to go down because we don't cross this axis again. Draw that a little bit better. So something like that. And because we cross here, the only option, because we're not going to go back through, is we're going to have to go up towards infinity. And you can verify this by picking another point, choosing something smaller than 1/2, in between 0 and 1/2. If you plug it into your function, you can plug it into this one or the reduced function I had written here, and you'll see that you're going to get a big number. And then the next thing you want to do is choose something bigger than 2. So let's erase this. Delete that. Okay, so I'm going to, let's delete this so I don't have to worry about it. So this is our function g of x is equal to x plus 2, 2x minus 1 over 3x, x minus 2. And let's plug in something bigger than 2, so let's go with 3. So we'll get 5, 9 on the top here over, hold on, let me redo that. So 3 plus 2 is 5, and then this will be 3 times 2 is 6 minus 1, which is also 5. 3 in here gives me 9, and then 3 minus 2 is 1. So we get 25 over 9, and we can put that in the calculator to get an estimate of what that is. It's 2.78. Okay, so when we plugged in 3, this asymptote is 3/2. Remember, that was the asymptote we found. Was it 2/3? I erased it. I think, let me just look back for a second. So it was, it was 2/3, sorry. So the asymptote was 2/3, and this number is much bigger than 2/3, which tells us that we're somewhere up here, and we're not going to cross this x-axis. Here we have a vertical asymptote, which we're going to go towards, and since we're not going to cross this axis, of course, we're going to have to go up like that. And then on this side, we could go a little bit down below it, but the overall idea is we're going to go towards this horizontal asymptote. Now let's compare this to a function when it's graphed on a graphing calculator. So let me pull this up. Okay. I'm going to erase our old function, and I'm going to put this one in. So it was y is equal to x plus 2, x minus 1, 2x minus 1. I believe that was right. Yeah, and then on the bottom, we have 3x, x minus 1, and x minus 2. So let's look at this function and compare it to what we had. You can see we definitely had, I'm looking back at the other function. Yeah, it looks very similar to what we did. You can see that we have an asymptote, and I believe that was at y is equal to 2/3. Yeah, you can see that right here. It's really close to that line. And then we also had the asymptote of 0, and I believe this one was 2. And then we had, you can see we cross at 1/2 like we had expected, and also at -2, 0. That's what we expected. And the rest of the graph, and we had this hole, which if we zoomed in, you'll see that we have the hole there as well. So it was at 1, there you go, 1 undefined. So we have a hole right there.